Let us continue our previous problem where we had taken just this is the plane wall. I will not again spend time on this, and we just solved for the at x equal to 0 what is the temperature. We got the temperature as 42.9 degree Celsius. So now what we will do is, what is the heat flux? The next question is, what is the heat flux? What is the heat flux in watt per meter squared at the plane wall at T equal to 8 minutes at the by convection how much it is losing, what is the heat transfer rate it is losing here, what is the heat transfer rate which is losing here, that is given by Newton's law of cooling. So I can write that Qx double dash at x equal to L comma 480 seconds, that is 8 minutes, 8 into 60 480 seconds is equal to QL double dash is equal to H into T of L comma 480 seconds minus T infinity. So I do not know the temperature at x equal to L, I need to find that. So theta at x comma t equal to T of x comma t minus T infinity divided by Ti minus T infinity is equal to A1 e to the power of minus lambda 1 squared Fourier number cos of lambda 1 x by L. For the same Biot number and Fourier number we have already gotten the lambdas, so I can just substitute that and get, so that is at x equal to theta comma 0 comma t, that is I can get this, so directly that is A1. What is my A1? A1 is, or this can be thought of as we have just found, that is theta of 0 comma t, correct, that is at x equal to 0 which we have found, or otherwise you can just substitute also if you are getting confused, there is no problem, that is 1.047 e to the power of minus 0.531 whole squared into Fourier number of 5.64 into cos of lambda 1 0.531 into x, that is L by L, that is 1 by x equal to L by L, that becomes 1. Now cos, this is in radians, so I have to convert this into degrees to operate your calculator. So I am multiplying that and dividing it by 180 by pi. So if you do this, and this is T at L comma 8 minutes minus of 60 divided by minus 20 minus 60. So I get T of L comma 8 as 8 minutes as 45.2 degree Celsius. So the previous temperature at the center was 42.9, at the wall it is 45.2, which is expected because the hotness of the oil is felt at the wall first, so it will be at the higher temperature. So now coming back, if I substitute this here, that is H is 500 into T of this is 45.2 minus of 60, that is equal to minus 7400 watt per meter squared. Okay, so this is what I get as the heat transfer rate. Now the last term what I need to get is the energy stored, energy per meter pipe of the length, pipe length, per meter pipe length being transferred after t equal to 8 minutes. So, for that I know q by q max equal to 1 minus theta naught wall into sine of lambda 1 by lambda 1. Okay. So, that is equal to 1 minus of, if you just go back and check this theta naught wall, actually this term alone reduces to 0.214. That is what I am going to substitute here. That is theta naught wall, that is 0.214. Theta naught wall is nothing but a1 e to the power of minus lambda 1 squared Fourier number. So, that is what I substituted, 0.214 into sine of lambda 1, that is 0.531 into 180 by pi. You now know why I am multiplying by 180 by pi, divided by 531. So, this comes down to 0.8. Now, Q max is equal to rho V Cp into T infinity minus Ti. So, rho is 7832 and volume is pi d into thickness, volume of the cylinder. So, how do I get that volume of the pipe? If I have to just show quickly, that is, this is what it shows, that is, volume is given by pi by 4 d naught squared minus di squared into L, and I can rearrange like this per unit length, that is per meter. So, L equal to 1 and volume I can this is pi into d naught by 2 and d naught plus di by 2 here, this is very small, d naught and di are almost same. So, I can take it as di. So, if I take that as di, so I can write this as pi di into 40 into 10 to the power of minus 3. Okay. So, that is what I have done. So, if I substitute that here, pi d into thickness, that is 7832 into pi into di is 0.04 into di is 1 meter and thickness is 0.04 into minus 20 minus 60. So, I get Q equal to minus 2.73 into 10 to the power of 7 joule per meter. So, we solved the plane wall problem, and we are now conversant with this solution what we have adapted. So, this was the exact solution for the plane wall. Now, let us see how does it translate to when we do it for the cylinder and also for the sphere. So, how does it look like? The temperature distribution for, now let me take up the cylinder, the temperature distribution for a cylinder. So, what is the figure for the cylinder? The cylinder is very large cylinder, this is, I mean large means longer length, and this is having R naught and this is radius R, okay, and this temperature T equal to Ti initially. Now, the question is, and again it is exposed to H comma T infinity. You can imagine this is the cylinder, this is the pen, so over which the flow is taking place, and we are interested in the temperature distribution T of R comma T. So, again without derivation we will have to get the temperature distribution as a function of Biot number, Fourier number, that is it. So, how does it look like? So, it looks that theta of R comma T is equal to T of R comma T minus of T infinity divided by Ti minus T infinity is equal to, only one term series I am writing, A1 e to the power of minus lambda 1 squared Fourier number into Bessel's function, that is J naught. This is a J naught, that is J naught is called 0th order Bessel function. I will write that J naught lambda 1 R by R naught. Don't have to worry, I will give the J naught value for a given Biot number and Fourier number, a Biot number. Okay, so this is the equation for theta. Now next is theta of theta naught t is equal to, so but before that, how do I get this a1 and lambda 1 for a given Biot number? That is given in the table. That's given in the table. If you just go back and see here in my notes, so if you just see here, for a given Biot number, what is there here is that for a given Biot number, we had used this table for a plane wall, but for cylinder, it is Biot number equal to, for a given Biot number, you can get lambda 1 and a1. But please note, for sphere or cylinder, it is actually h r naught by k. So you can get lambda 1 and a1 for both cylinder and sphere. Okay, and this is for different Biot numbers, it will go on. Okay, so that is what you are going to get for, this is what is going to be for cylinder, and this is the equation for sphere. I will write both the equations and reduce it for the plane wall. Okay, so now the theta of 0 comma t, theta at 0 comma t is t of 0 comma t minus t infinity divided by ti minus t infinity is equal to a1 e to the power of minus lambda 1 squared Fourier number, because Bessel's 0th order Bessel at 0 is 1. Okay, that you can check in the table as well. If you just go back and see in the table also, you are going to get that. Now let us write for sphere. Similarly, we can write for sphere. For a sphere, the this is my sphere and this is the radius r naught and this is my r, and everywhere it is experiencing h comma t infinity. So theta of r comma t is equal to t of r comma t minus t infinity divided by ti minus t infinity is equal to a1 e to the power of minus lambda 1 squared Fourier number into sine of lambda 1 r by r naught divided by lambda 1 r by r naught. You see something very interesting here. The temperature variation with time always is exponential, whether it is plane wall or cylinder or sphere. Only the space variation function is varying. Please note that. Similar to here, theta of 0 comma t is t of 0 comma t minus t infinity divided by ti minus t infinity is equal to a1 e to the power of minus lambda 1 squared Fourier number. You know that in plus 2 you have studied limit as r tends to 0, this becomes equal to 1. So that is why you get this temperature distribution. Now the next question is, what is the heat transfer for cylinder and sphere? So for cylinder it is Q by Q max equal to 1 minus 2 theta naught cylinder into J1 lambda 1 divided by lambda 1. So J1 is the Bessel function, first order Bessel function. J1 is the first order Bessel function. You don't have to worry about that function because the values are given in the form of a table. Now for a sphere, Q by Q max is equal to 1 minus of 3 theta naught sphere into sine of lambda 1 minus lambda 1 cos lambda 1 divided by lambda 1 cube. So, we have gotten the temperature distribution and also the energy transferred. So, these one term solutions are valid under certain circumstances, that is at T equal to 0 temperature is Ti and it is uniform throughout the body, okay, and the heat transfer coefficient H is constant and also T infinity is also constant, it does not vary with time, and there is no energy generation term, then only these solutions what we have given are valid. So, what we will do is, now we will take up a simple problem where we have to do with sphere, that is I will take egg, I will take a problem of an egg, that is an ordinary egg can be approximated as a 5 centimeter diameter sphere, okay. The egg is initially at a uniform temperature of 5 degrees Celsius and dropped into boiling water at 95 degrees Celsius. Why 5? Because you take your egg from the refrigerator, so the temperature typically is around 5 degrees Celsius and dropped into your boiling water which is around 95 degrees Celsius. Taking the convective heat transfer coefficient between the egg surface and the water, boiling water, as 1200 watt per meter squared degree Celsius, determine how long it will take for the center of the egg to reach 70 degree Celsius. So, although egg is not truly spherical, we are going to consider this egg as sphere. So, let us see how do we solve this problem. That is, I have an egg and its initial temperature is 5 degrees Celsius and H is equal to 1200 watt per meter squared Kelvin and T infinity is 95 degree Celsius. And now the question asked is to reach at the center T naught as 70 degrees Celsius, what is the time taken? And we are approximating this egg as a sphere of diameter 5 centimeter. So, with this let us see how do we get the properties. The properties of the egg are like water properties only. I should take any living substance. If you do not have any properties, including me, human body, if I do not have the properties, I have to take the properties of the water, because most of the volume of my or the mass of my body is made of water. Similarly with the egg also. So, egg is 74% is water content. So, the properties of the water are taken at 5 plus 70 by 2, that is Ti plus T naught by 2, that is 75 by 2, that is 37.5 degrees Celsius. So, at 37.5 degrees Celsius, I get a K of 0.627 watt per meter Kelvin and an alpha of 0.151 into 10 to the power of minus 6 meter squared per second. Now, I cannot calculate Fourier number because time is what I need to calculate Fourier number, because what is the time taken is what I need to find. So, next thing I can do is Biot number H R naught by K. H is given to be 1200, R naught is diameter is 5 centimeters. So, 5 into 10 to the power of minus 2 divided by 2 because the radius, and the thermal conductivity is 0.627. So, you get a Biot number of 15.95. This also means that this is not lumped, because Biot number is pretty much greater than 0.1. Now, in fact, the you should, if you have to calculate the lumped, LC equal to volume by surface area, volume by, this is d by 6 you get for a sphere. So, you get 5 into 10 to the power of minus 2 divided by 6. Actually lumped criterion will still be lower than, will be still greater than 15.95 even then, that is Biot number HLC by K if you put, that is 1200 into 5 into 10 to the power of minus 2 divided by 6 divided by 0.627 will be around 15.95 divided by 3. So, still this will be very high. So, point is Biot number will be higher than 0.1 and it is lumped. So, if this is lumped, then I have to take the one term series solution. For the center of the sphere, if you recall, we have theta of 0 comma t equal to t of 0 comma t minus t infinity divided by ti minus t infinity is equal to a1 e to the power of minus lambda 1 squared Fourier number. Okay. So, I have to get for Biot number 15.95, I have to get the values of lambda 1. So, if you just come down, so this is indeed 15.95, this is indeed 15.95. So, this is 15, this is LC, this is LC. LC. So, you get this is 5 into 10 to the power of minus 2 divided by 6, you get a Biot number greater than 0.1. But now for this calculation, I have to calculate Biot number as H R naught by K. So, H is 1200 into 5 into 10 to the power 5 into 10 to the power of minus 2 divided by 2 divided by K of 0.627. So, the Biot number happens to be 47.8. For this 47.8, I need to get the lambda 1 and A1. So, if you really see here, so for a Biot number of 47.8, if you do the interpolation between 40 and 50, I am not going to do the interpolation because I have shown that in the previous class. So, you get lambda 1 as 3.0753, which is in between these two, A1 as 1.9958. So, if I take that value, so you will get lambda 1 Biot number at 47.8 from the table, you get lambda 1 equal to 3.0753 and A1 equal to 1.9958. So, you get at the center theta of 0 comma t is equal to t of 0 comma t minus t infinity divided by ti minus t infinity is equal to a1 e to the power of minus lambda 1 squared Fourier number. So, if you just substitute, this is 70, the center of the egg should be 70 and this is 95 boiling water divided by initial is 5 minus 95 is equal to 1.9958 e to the power of minus 3.0753 into Fourier number. So, I get Fourier number of 0.209. Luckily, Fourier number is greater than 0.2, only one term is sufficient. One term is sufficient. So, now Fourier number equal to, I need time, alpha t divided by L squared. So, alpha, what is alpha? Alpha we have found 151 into 10 to the power of minus 6 t divided by L squared, that is 2 point, that is here in this case it is going to be R naught squared. R naught is 5 into 10 to the power of minus 2 divided by 2. So, it is 2.5 into 10 to the power of minus 2 whole squared, okay, is equal to 0.209. That fetches me t equal to 865 seconds, that is approximately 14.4 minutes. So that means for the egg to boil, I have to keep under this condition for at least 14.4 minutes. So that's how we could solve this problem. So we have covered in today's lecture, what did we cover is that, if you just recall, so what we gave is the temperature distribution for we said that exact solution will be of this form, okay, and we gave for plane wall, cylinder and a sphere. And the temperature distribution, as you can see, what is so beautiful here is that the temperature variation with time irrespective of plane wall, cylinder and sphere is exponential, which is the same as what we had gotten in lumped body. Now in a plane wall it varies as a cost function, in a cylindrical wall, in a cylinder it takes a Bessel function, and in a sphere it is signed by lambda. So this is how we get the temperature distribution. To get this A1 and lambda 1, I need to get the Biot number. Once I know the Biot number, I can get the lambda 1 A1 for plane wall, cylinder and sphere. The most important thing I want to re-emphasize is that for Biot number for plane wall it is HL by K, and for cylinder and sphere it is HR naught by K. Remember that this Biot number is different from the Biot number what we defined for lumped body. For a lumped body it is HLC by K, where LC is volume by surface area. You are not supposed to take volume by surface area when you do this plane wall or cylinder or sphere for spatial variations in time, okay. So, and for one term approximation is valid for Fourier numbers greater than 0.2, and at the center of the plane wall, all these at the center of the plane wall, it is only going to vary exponentially for all the cases, okay. So now very interesting case we come across is that if you go to this table, for a Biot number infinity also there is a value given. If the Biot number, that is, how can I realize Biot number infinity as an engineer? Biot number infinity implies that heat transfer coefficient is very large. So when will this occur? When will the heat transfer coefficient is very large? If you recall in my introduction slides, we have said that for boiling the heat transfer coefficient will be of the order of 50,000, 60,000. So in that case, the 1 by Biot number, that is K by HL, will become 0. K by HL will become 0. That is, I can consider that Biot number as infinite. So in that case, for boiling, or if the heat transfer coefficient is very large, what does that mean? So let's understand this little slowly. So actually if the heat transfer coefficient is very large, 1 by Biot number is 0, it actually becomes constant wall temperature, okay. So this I will explain in the next class in more detail, what is the physical implication of Biot number infinite, and subsequent to that we will take up in the next class what is called as the transient heat conduction in semi-infinite solids. Thank you.